All right, today we're going to talk about pH and what that means in terms of the concentration of hydronium ions and hydroxide ions. First, we're going to talk about something called self-ionization of water. We said earlier that water is amphoteric and can act as either an acid or a base. Well, in pure water, this reaction happens. One water molecule accepts a hydrogen to become the hydronium ion, and one molecule donates a hydrogen ion to become the OH ion. So in any sample of water, there will be a little bit of each of these ions present. The self-ionization constant gives us an idea of how much of these things are present. The value is 1 times 10 to the minus 14th, and it is equal to the hydronium ion concentration times the hydroxide concentration, whether it's an acid, base, or neutral solution. So the constant is 1 times 10 to the minus 14th. In pure water, the hydronium concentration is 1 times 10 to the minus 7th moles per liter, and the hydroxide concentration is 1 times 10 to the minus 7th moles per liter. So most of your water exists as molecules, but a very, very small amount breaks up into those ions. The pH scale is a way to express how basic or acidic something is, and it's based on the log of the H3O concentration. So we need to review what logs are for a minute. If we take the number 10,000 and write it in scientific notation, it's 10 to the 4th. That 4, the exponent, becomes the log. The log of 10,000 is 4. If we write 0.001 in scientific notation, it's 10 to the minus 3rd. That minus 3 is the log of 0.001. So for acids and bases, the Kw still has this value, but the amount of hydronium and hydroxide ions will vary. So to calculate pH, we take the negative log of the hydronium ion concentration. Because it's on a log scale, 1 unit change from 7 to 6 or 7 to 8 is a tenfold change in the hydronium ion concentration. So if the pH is 1 to 6.9, we call it an acid. pH 1 is very acidic. 6.9 is very slightly acidic. When it's 7.1 to 14, it's basic. 14 is very basic. 7.1 is only slightly basic. And when pH is 7.0, it is absolutely neutral. So we're going to look at pH and the concentrations of hydronium ion and hydroxide ions that are present. So for whole number pHs, we're going to get 1 times 10 to the minus something as our H3O concentration. So pH 7, absolutely neutral. H3O, 1 times 10 to the minus 7th. Hydroxide, 1 times 10 to the minus 7th. So the OH and the H3O concentrations are equal to one another. As pH goes up, 7, 10, 12, 14, the amount of hydronium ion present is decreasing. So when you put these numbers in regular notation, you get an idea of how very, very small the concentration of H3O is at a pH of 14. As you go down in pH, -6, -5, -4, those numbers are getting larger. So again, when you put it in regular notation, you can see how much the concentration of the H3O is increasing. So at pH 1, you have almost all H3O and very little OH. So now let's look at the OH concentration. As pH goes up, 10 to the minus 7th, 10 to the minus 4th, 1 times 10 to the 0, that OH concentration is increasing. So again, if we look at the regular numbers, you can see that that OH concentration is increasing. At pH 14, very, very, very little H3O, but a lot of OH. Going the other way, as we go down in pH, the OH concentration is getting less and less and less. If you want, you can fill this in from the PowerPoint rather than having to do it while this video is running. So let's talk about pH and what kinds of compounds are acidic and basic. So pure water is absolutely neutral. pH 7, 10 to the minus 7th moles of H3O, 10 to the minus 7th moles of OH. As pH, now we have the scale going the opposite way. pH is going down as we go from 7 to 0. It's becoming more acidic. So here are some things that are mildly acidic. We call them weak acids. They don't ionize completely. So milk, very slightly acidic. Bananas, tomatoes, apples, moderately acidic. As the pH gets lower, lemon juice and vinegar. Remember, while we're not going around tasting acids in the lab, we said that acids taste sour. So because they contain a fair amount of acid, lemon juice, vinegar are acidic. Stomach acid has a pH of about 2. Now, not to be gross, but the acids are needed in your stomach to aid digestion. I know we've all vomited at one time or another in our lives. And did you ever notice that when you vomit, your throat burns as that vomit is coming up? That's because that stomach acid, your stomach is built to withstand that acid. If it doesn't, you get ulcers. But your throat and your nostrils are not. So it's not a real pleasant thing when you vomit up stomach acid. Even more acidic than that, your car battery has battery acid in it, which is very concentrated sulfuric acid and also concentrated hydrochloric acid, are very acidic, have very low pHs. On the other side, as pH goes up, your blood is very mildly basic, pH of about 7.2 to 7.4. Baking soda may be pH of 8. These are weak bases. They don't ionize completely. So you may be familiar with Tums being called an antacid. Well, Tums is basic. So if you have too much stomach acid and your stomach is not feeling good, you can take an antacid, which will neutralize some of that stomach acid, bring the pH back up a little bit, and your tummy will feel better. Soap is moderately acidic. Soap is moderately basic. Ammonia, moderately basic. Then you get down into the really high pHs, a lot of hydroxide present, very little H3O. Drain cleaner that we use to unplug our drains is very basic, and concentrated sodium hydroxide is very basic. So what we find is things in the middle are okay with our bodies, but as we get very, very acidic, very dangerous to human tissue, and as we get very basic, very dangerous to human tissue. Your assignment is going to be to fill out the pH molarity chart, which I will assign. And all the slides that I've shown here in this video are part of the PowerPoint on acids and pH, which is posted in the acid resource folder.